Okay, so welcome to lecture 29. So we have started our discussion on constitutive relations, okay, which we are going to continue. Just to give you a recap, let me write down all the equations that we have derived till now. So we have mass continuity, then we have linear momentum balance, then we have angular momentum balance, then the first law of thermodynamics, okay, and then we have the second law of thermodynamics, right, which we wrote in a slightly different form using Helmholtz free energy. I'm just going to write that here. Okay, so these are the equations that we have derived. There are no further equations. Okay, so if we look at what are the unknowns and what are the prescribed quantities, then B is something that will be prescribed externally. Likewise, small r, okay, that's just a scalar. So that's going to be prescribed externally, and I guess nothing else. So these are prescribed externally. Then what are the unknowns then? We have rho, then we have velocity, then we have sigma, and d is in terms of velocity, right? D is the symmetric part of velocity gradient. Then q is also an unknown. Epsilon, the internal energy density, specific internal energy is also an unknown. Specific Helmholtz free energy, then the entropy function eta, and finally temperature theta. Okay, so we have so many unknowns. And how many equations do we have? 1, here 3. So this is 1, this is 3, this is also 3, this is 1. And this is just an inequality. It's not really useful in solving an unknown, but it just provides some restriction. You will see later on. So we have total 8 equations. And look at the unknowns. 1, 3, 9, 3, 1, 1, 1, 1, 1, 2, 3, 4, 3, 7, 9, 16, 3, 19 plus 1, 20. That's a lot of unknown, right? So that's where the need of constitutive relation arises, right? This was also a question yesterday. So we have to know sigma. We have to know a function for sigma. Let's say sigma hat in terms of kinematic quantities. which could be your rho or the deformation map y hat or theta. Okay. Similarly, we need, in fact, since it's a specific, so sigma hat, and since then we have q, we likewise need constitutive relation for q, then for internal energy, specific internal energy, then specific Helmholtz free energy, entropy, specific entropy, and finally temperature. Well, temperature is a basic unknown, so we don't need any constitutive equation for these. So how many constitutive equations? For sigma hat, we have 9, right? 9 components. Of course, if you assume symmetric, then the equations, number of equations also reduces, right? If you using A and B symmetry, then only 5 equations remain, and likewise here 9 goes to 6 then. Okay, so similarly here also this 9 will go to 6 if we have already assumed symmetry of the stress tensor. Then here we have 3, here we have 1, 1, 1, and you'll see that it will all finally together, it will be such that the number of unknowns will be same as the number of equations. The basic unknowns are basically rho, y hat, and theta. Once the constitutive equations are prescribed, then the basic unknowns are just rho, y hat, and theta. And the equations that which will be required would be the continuity equation, then the linear momentum balance, and finally the energy equation. Okay, so these are the equations which will be needed for the 5 unknowns. And this is, of course, we are describing in the Eulerian form. You can likewise think of the Lagrangian form. Okay, 5 unknowns and 5 equations. We are not putting A and B here because we have chosen a constitutive relation which automatically satisfies A and B, so we don't put it explicitly while solving the equations. Okay, so I hope this thing is clear to everyone so far. Okay, there is no query till now. Okay, so then comes the question about how should the constitutive equation look like? What can be the various restrictions on the constitutive equations? Okay, so these constitutive equations that we have listed here. So there are some basic physics principle which should not be violated when we choose a constitutive relation. Okay, it can't be arbitrary. It has to satisfy the laws of physics. Okay, number one is what is called causality. This, by the way, is I think it's in chapter 7. Yes, it's in chapter 7 of the textbook. So number one is causality. So some of you may have heard about this term, but what it tells us is that the all these sigma, q hat, epsilon, psi, or eta, they cannot depend on the future values of the unknown field variables, that is rho, y hat, and theta. That makes a sense, right? whatever is happening now cannot depend on what's going to happen in the future. Okay, so that's causality. So we just say that current value of filled variables cannot depend on future values. Okay, that is making sense, right? You might think, oh, why are we even discussing this? But it's good to at least know that this is also something which is there. Okay. The second thing is the filled equations that we have up there. The constitutive equations should not violate the filled equations. Constitutive equations should not violate the filled equations. And if you look above, no, then all that it means is that the A and B, the conjugate equation must be such that your sigma is symmetric. We have to choose an equation such that sigma is symmetric. And finally, the second law of thermodynamics. Rest all never get violated. You can choose arbitrary conjugate equations. Mass continuity still will not get violated, or LMB does not get violated. And the reason being that in LMB, so let me say this again. So what I have written here is that constitutive equation should not violate the filled equations. So that means it cannot be arbitrary. It must be such that filled equations are also satisfied. Now, if we look at the filled equations, number one is mass continuity. You see that in this equation, none of the constitutive variables are present. Sigma, Q, epsilon, psi, or eta. So mass continuity filled equation does not put any restriction on the constitutive equation. Then if you look at LMB, it has sigma in there. So what we are trying to say is that sigma must be such that it must obey the LMB. It cannot violate the LMB. But it turns out even LMB does not put any extra restriction on the function for sigma because of the presence of B. So whatever sigma you choose, in the constitutive equation, you can always think of a body force B so that this gets satisfied, the LMB gets satisfied. See, B is something which is externally prescribed, isn't it? So you can choose any value for sigma, and for that particular sigma, you can then later on choose a B so that LMB gets satisfied. So LMB also does not put any restriction on constitutive equation. Okay. Then A and B, yes. A and B means that your sigma must be symmetric. Okay. So it does put a restriction. Then energy equation, it turns out energy equation also does not put any restriction, because you see you got some sigma from up there, then D is kinematics, then you have Q here and epsilon here. So again, you can choose any function for Q, epsilon, and sigma. And for such a choice for sigma, Q, and epsilon, you can then choose a R, the heat generation per unit mass, small r, heat generation rate per unit mass, so that energy equation is also getting satisfied. So again, this also does not put any restriction. And finally, you see, you come to second law of thermodynamics, this inequality. So you have already chosen your sigma, q, epsilon, and then you come to the second law of thermodynamics. So now there is nothing external thing. For example, you don't have a small r sitting here, or you don't have anything like b sitting here, which you can use to get this inequality satisfied. So therefore, it's only the second law of thermodynamics, or this inequality, which essentially puts a restriction on the constitutive equation. It is just the inequality corresponding to second law of thermodynamics. And EMB, okay, which places restriction on constitutive equation. Okay, if you have any query, please feel free to interrupt me. Okay, then finally is the objectivity. This is another thing. We have been discussing this. The constitutive equations must obey the principle of objectivity or frame indifference. Okay, whatever is the constitutive equation, it should be independent of the frame of reference. A very simple thing, for example, is the response of a spring. The force, internal force in the spring is equal to the spring constant times the elongation of the spring. Now this is, like constitutive equation for the spring. And this equation does not change when you go from one frame to the other. Irrespective of what frame you are looking at, the force in the spring is equal to spring constant times the elongation of the spring. Now this is like a scalar constitutive equation. We have to talk of tensor constitutive equation. So whatever is the equation of whatever constitutive equation we choose, the equation must be such that as you go from y to y star, no? So you go from yt to y star comma t star such that y star is equal to q of t into y plus c of t. So when you undergo this transformation, the equation must likewise undergo the transformation in the way we have discussed. If it has some vector, like I said, whatever is the equation, the terms present in the equation must transform as per the equations that we had listed. So for example, if it has a vector v, then it must transform to q times v. If the equation has a tensor A, it must transform in the way QA Q transpose. Okay. Or if it has a scalar alpha, it simply goes to alpha. So the equation must be such that it obeys this transformation. Then only we can say that the equation is frame indifferent. Okay. let's talk about what else it should satisfy. And I'll just give you one example. For example, if we say that the internal energy response function epsilon hat, if we say that it depends on deformation gradient big F and theta, then when we go from y to y star, we know that F changes to QF, isn't it? But also epsilon being a scalar variable, epsilon star must be same as epsilon, right? So that means epsilon hat star as a function of f star comma theta star must be equal to epsilon hat. But since the constitutive function has to be the same, right? Like we said, so epsilon hat star is same as epsilon hat. The function, because it's a scalar, no, so it has to be the same. And then f star is then q of f, right? We know that. And theta star is same as theta. So objectivity simply tells us that the constitutive equation or constitutive function for internal energy must be such that epsilon hat of f comma theta is equal to epsilon hat of q of f comma theta. Okay. All right. So having discussed that, we proceed further. Then there is something called material symmetry. It has got to do with microstructure of the material. You know that there are materials which are, for example, isotropic, or there are materials which are orthotropic or transversely isotropic, or there are materials which have crystal symmetry. So the energy function, for example, or any of the constitutive equations functions must be such that it obeys material symmetry. It's a very important topic, and we'll discuss this in depth later on. So it has got to do with why a function is isotropic or transversely isotropic or orthotropic. Then also, something about internal constraints. If the material has any internal constraint, then the constitutive equation must satisfy that internal constraint, must obey. For example, if the material is incompressible, then the constitutive equations or constitutive functions that we have chosen must be such that it does not violate the constraint of incompressibility. Okay. And finally, another thing is what is called equipresence. So what it means is that, you see, for example, we have the constitutive functions for sigma hat, then epsilon hat, eta hat, q hat. So if we say that sigma hat, for example, depends on deformation gradient, then we simply say that all of the others also depend on deformation gradient. Similarly, if we say that sigma hat depends on f dot, then to begin with, we'll say that all of them also depends on f dot. So that's the meaning of f equipresence. So dependence on a particular variable must be present in all the constitutive equations or all the constitutive functions. Okay. Okay, then let us talk about this is all just going abstract. Let us think of some examples. So different forms of constitutive response functions. So there can be a constitutive response which depends on only the current state of the material or current state of the body. Or there can be a constitutive response which also requires dependence on how the material has evolved with time. Okay, so we say such materials as materials having memory or no memory. So materials with memory, so it's a fancy word, materials with memory. It means the constitutive equation or the response of the material is such that it remembers how it has evolved in time. Basically, for example, if you think of sigma hat constitutive function, no, and at time t, then so sigma at time t would be such that we have a constitutive function sigma hat, which depends on the y hat for all time from 0 up to t. So this is called a material with memory. So it knows, so I mean it has to know how it was on all the back time in order to decide what it will behave, in what way it will behave currently. Okay, then you can have materials with no memory. That means sigma at time t will depend on, it will have a constitutive function such that it only depends on y hat at the current time. So sigma at time t just depends on the current deformation. Does not depend on how the deformation was in the previous time. Okay. And then, in the memory also there are two cases. One is short-term memory and then you have long-term memory. So you can guess what's the meaning of them, right? So short-term memory means it only depends on the history, but up to very small time. Whereas long-term means it depends on a very large history. Okay. Likewise, you can have, materials with local versus non-local. I'll say local constitutive form versus non-local. So what this means? It means, for example, if you are again talking of the response for sigma, the constitutive function for sigma, then it will be such that, and say I want sigma at the location x, okay, and at time t, then local means the function will be such that, and let us say it depends on deformation gradient, for example, then this function will be such that it only depends on deformation gradient at the location x and time t. Whereas non-local would mean you have a response function such that it depends on f for all y in some neighborhood of x. So suppose this is a body and you are looking at point x, then the response at x depends on some neighborhood of x. So on the values of y in the neighborhood of x. So that's non-local constitutive form. But if the response depends only on the value at x itself, so response at x depending on the value at x itself, that means it's a local constitutive form. Okay, so that's local versus non-local, or memory versus no memory. I hope that this is clear to all of you. So you can of course get more deep into it if you read the textbook. Okay, this is by the way section 7.1 in the textbook. So there is a lot more description, some more mathematical formulas given there. So I'm not going to do that here. Next, we'll just give an illustration. It's a warm-up to a more general theory that we will perhaps cover in the next lecture. Today, we are going to illustrate how, whatever we said above, how, for example, the second law of thermodynamics indeed puts restriction on the constitutive form. We'll just illustrate how, starting with a general function, using objectivity and second law of thermodynamics and A and B, we are able to come up with a very specific form of constitutive equation. Okay, so we are going to illustrate that today for a simple material. So let us think of purely mechanical motion. Let us think of purely mechanical motion. That means there is no heat flow going on, or you can say that the temperature of the body is uniform and it is not changing with time. So that we say it's the purely mechanical motion. So I'll say here no heat flow. Theta is homogeneous and does not change with time. So if that is the case, how will the equations finally modify? So the equations, the continuity will be same, all the equations will be the same, but some of the equations will get trivially satisfied. Okay, so for example, your aim, this mass continuity remains as it was earlier. So you have rho dot plus rho times divergence of velocity, that's equal to 0, and you know that in Lagrangian form it is rho naught equal to rho times j. Then you have LMB, which remains of course the same as earlier, that is sigma plus rho plus the body force B, that's equal to rho times V dot. Then you have the AMB, and then you don't need energy equation. Okay, for purely mechanical motion, energy equation is not required. it gets trivially satisfied basically. So if you look at the energy equation, there won't be any small r term, there won't be any q term, and then this you simply have rho epsilon dot equal to sigma double contraction d, and this will just tell you how epsilon is changing with time. But then you don't need to know how epsilon is changing with time. All that you need is rho and velocity. Okay, so energy equation is not required. Likewise, if you talk of the second law of thermodynamics, it indeed gets simplified greatly. So it has theta dot, you see it's not going to be there. Then theta being homogeneous, this term is also not there, and q is also not there. So you have only the first two terms present. Okay, which means the second law equation simply reduces to rho psi dot being less than equal to sigma double contraction d. Okay, so how many unknowns are present here now? Have a look at the number of unknowns. So you have rho, then velocity, then sigma, and psi. Okay, and equations, you have 3, 3, 1. Suppose I say that I enforce sigma to be symmetric, then we can forget about A and B, and we just have mass continuity and LMB. Okay, so I'll just say sigma chosen symmetric, then we just have mass continuity and LMB, which can cater for rho and V. So we need response for sigma and for psi. Okay, these are the things which are required. And as I said, we'll do a specific case, and it's a purely mechanical motion. So let's think of what is called compressible inviscid flow. Okay, compressible inviscid flow. There's no viscosity present, there's no, it's inviscid, okay, inviscid flow, but it is compressible, not incompressible. So, in such a case, it turns out you can say that sigma depends on just J, and psi also depends on just J, okay, where J is determinant of F. And also for such a flow, the material has no memory, okay, and it's local in nature. And that is why you see that sigma depends on J at the current time and at the same location. So sigma of x comma t, I'll make it more specific. Sigma at x comma t is simply the sigma hat g of x comma t at the same location and at the same time. And likewise goes for psi. So it's basically, we have chosen a function which is local and without memory. Okay, so far so good for everyone. Okay. All right, so let's see how we can, you see right now to begin with, how many functions do we have? We have 6 in sigma because we have assumed it's symmetric, and 1 in psi. So we have 7 unknown functions to begin with. And let's see how frame indifference and second law of thermodynamics, how do they put restrictions? So let's first talk of frame indifference. Okay. All right. So from here, so if you go from y to y star, so what frame indifference says that the constitutive response has to be also objective. So psi hat of star j star then should be same as psi hat of j, right? Because psi is a scalar, so psi hat star of j star should be same as psi hat of j. But what is j? J is determinant of f. So j star is then determinant of qf, right? Which is same as determinant of q into determinant of f. But q being a rotation tensor, determinant of q will be equal to 1, so it is same as j. So j star is same as j. So this implies your psi hat star, which has to be same as psi hat, right, from the constitutive assumption. So psi hat and j star is also same as j. So this basically gets automatically satisfied. Because j star is same as j, it gets automatically satisfied. So the fact that psi hat is just depending on j is it satisfies the principle of frame indifference or objectivity. So for psi hat, it does not put any restriction. Okay. Now let's talk of for sigma. So sigma, we said that it is this function sigma hat depending on again j. So what will be sigma star then? For the another motion, sigma star will then be that function, response function sigma hat depending on j star, right? Because the function that we have chosen will be same for all the motions. So the hat function is the same. You see, it is the same here. So basically, the function sigma hat is same as sigma hat star. That's we have chosen it same because the function has to hold for all the motion. So it is irrespective of objectivity. The constitutive function that we have chosen has to hold for all the motion. Okay, so sigma hat function and sigma hat star function will be the same. That doesn't mean that we have employed objectivity. It is irrespective of objectivity. Okay, now, so how is this then going to put any restriction? But you know that sigma star, looking at this, sigma star is equal to sigma hat, and but j star is same as j, right? So this implies that sigma star is equal to sigma hat of j because j star is same as j. But sigma hat j is also equal to sigma, isn't it? From here, please ask me if you're not able to follow anything. Now, if because sigma has to transform, you know that the way sigma transforms, this we know this is equal to q sigma q transpose, right? So what we have finally gotten is that Q sigma Q transpose must be equal to sigma. This is what we are getting when we employ objectivity for this particular response function. When we employ objectivity, we are getting that Q sigma, this is the restriction that we are getting, Q sigma Q transpose being equal to sigma itself. So when is that possible? Now this is not possible for an arbitrary sigma. This is possible only if sigma is proportional to identity. Only then this can be possible. So I'll write here it is possible if and only if sigma is proportional to identity. So this is indeed putting a restriction. So what it says is that if we say that sigma response function only depends on J, then employing objectivity, it says that you cannot have 6 arbitrary functions here. The sigma will be such that you have just an scalar response function, okay, which we will denote by the pressure function p hat depending on J times identity. So this is coming from objectivity, which says that if we are assuming that the constitutive function for sigma hat only depends on J, then objectivity implies that function must be of this form. So sigma hat must be of this form. And can you see that indeed this is the case in compressible fluid flow? When you have compressible fluid, the only constitutive dependence is on pressure function, and stress is always proportional to identity. Compressible in viscid flow, stress is proportional to identity. Okay, so far we have gotten, so objectivity implies sigma hat to be of this form, but for psi hat it does not put any restriction. Psi hat is just depending on J. Okay, and also you see that usually it is written in a slightly different form, because we know that from mass continuity rho naught equal to rho times J. So dependence on J is equivalent to saying that it depends on rho, current density. So that means you can write your sigma hat function to be minus p hat of rho identity, and psi hat function to be just psi hat of rho. Okay, so you see that starting with 7 unknown functions, we have now just 2 unknown functions. Only 2 unknown functions now for p hat and psi hat. So that's a restriction from objectivity. Okay, now let us see what's extra restriction are we going to get, because we haven't yet employed that entropy inequality, So restriction due to entropy inequality. Let us see what we get from here. So in the entropy inequality, if we just have a look at it, for purely mechanical motion, we have rho psi dot less than equal to sigma double contraction d. So rho psi dot less than equal to sigma double contraction d. Okay, or we simply say rho psi dot minus sigma double contraction d is less than equal to 0. Now we plug in the constitutive form, so we have rho del psi hat by del rho into rho dot, isn't it? Because psi hat is a function of rho, so we can write that. So psi dot is simply, or in fact, this del psi also becomes d psi. So d psi hat by d rho into rho dot. Minus for sigma hat. So sigma hat we have just seen, we wrote it as minus of p times identity. So it becomes plus the pressure function p hat of rho times identity double contraction d, which is the symmetric part of velocity gradient. So that's gradient of v plus gradient of v transpose by 2. So this has to be less than equal to 0. So this is further rho d psi hat by d sigma into rho dot plus p hat of rho. And you see, when you do double contraction of I and this gradient, you will simply get divergence of velocity, isn't it? But then divergence of velocity from mass continuity rho dot is equal to rho times divergence of velocity, isn't it? So if you plug that in here, you have rho times d psi hat by d rho into rho dot plus p hat of rho into rho dot by rho less than equal to 0. Okay, so I hope I haven't made any mistake anywhere. Sorry, this is rho dot plus this equal to 0, so you get a minus sign here now. I was thinking, where is that minus sign? Okay, here it is plus, but here you'll have a minus sign. So finally, this tells us that it is rho square d psi hat by d rho minus p hat into rho dot that's less than equal to 0. Okay, so we are almost done. Now you see, in this inequality, your rho dot can be either positive or negative. Rho dot can be anything, the change in rho. So for this inequality to be satisfied, the thing inside the bracket must be equal to 0. Or what this means is that this p hat is equal to rho square d psi hat by d rho. So that's the restriction from second law of thermodynamics, that even the pressure function and the psi hat function, they can't be independent. Pressure function must be equal to rho square d psi by d rho. You see that finally, using those restrictions, you are able to boil down to just one unknown constitutive function for psi hat. If you know psi hat, you can know sigma. Because if you know psi hat, take the derivative, you get p hat, and from p hat, you then have sigma. Okay, so this is an illustration of how constitutive equation can be used to obtain restrictions on constitutive, sorry, how restrictions can be used to get more information about constitutive equations. Okay, so I'm going to stop here, and we'll meet again in the next class.